In this second video for simple linear regression and correlation methods, we are going to find out what happens to our goodness of fit line and our sum of squares total, or the total errors, if we consider the independent variable in analyzing the trend in our dependent variable. So if you can remember, in our previous video, we only used the dependent variable amount of mass lost, and we did not use the time element, exposure time with the bacterium Serratia liquefactions. So before we continue, when we now consider two variables as opposed to just one, we are going to be calling now our goodness of fit line as the regression line. Okay, so in the previous video, I think we ended with the goodness of fit line being perfectly horizontal like this by just using the mean of our dependent variable as a predictor to something that's slanted like this, positively sloped or positively sloping. Okay, if you can remember, we had a strong positive relationship for the Pearson correlation coefficient as well. So this line now that is slanted is now our regression line. Okay, so this regression line is defined, of course, just like in algebra, by a slope and by a y-intercept. So these are the formulas for the slope and the y-intercept of our regression line. So you don't need to worry about all of these notations here. We are going to get them one by one. So first, let's look at this table. In the previous video, we have been acquainted with these two variables. Okay, our independent variable, the exposure in days, that's X, and our dependent variable, the mass lost from our chitin exoskeleton, that's Y. Okay, so first let's get the mean for the time or the exposure to the bacterium Serratia liquefactions. So we are going to add everything here in our first variable and divide by 5, and we are going to get 1.46. Next, we are going to solve for deviation of the days from the mean that we just solved, 1.46. So we have 0.5 minus 1.46, and that's negative 0.96. And then we have 1 minus 1.46, and that's 0.46. And then we have 1.5 minus 1.46, and that's 0.04. And then 2 minus 1.46, that's 0.54. And then 2.3 minus 1.46, and that's 0.84. Next, we are going to get the mean for the mass lost, okay, this time for our dependent variable. So we are going to add all of these values and divide by 5, and we get the value of 1. This is what we had in the previous video, if you can remember, our best estimator. Okay, and then we solve for column number 4 here, this one. Okay, so we have 0.6 minus 1, that's 0.4. And then 0.7 minus 1, that's negative 0.3. And then 1 minus 1, that's 0. And then 1.2 minus 1, that's 0.2. And 1.5 minus 1, that's 0.5. Next, we are going to get the products of these two deviations. Okay, so we are going to simply multiply these values. So for the first row, we have negative 0.96 times negative 0.4. That's positive 0.384. And we are going to do that with the other 4 rows. Okay, so these are simply the products. Okay, and then we are going to get the summation of this column. So we're going to add everything, the summation for that. And notice that's what's here on top. Okay, so once we solve for the summation here, that's the numerator for our slope, 1.05. And then we are going to get the square of the deviations of the days. Okay, so meaning to say, this third column here, this one, we are going to square each one of these. So negative 0.96 squared, that's 0.9216. And then we have negative 0.46 squared, that's 0.2116, and so on. And then we are going to get the summation of this as well. And notice that's the denominator of our slope here. Okay, and that's 2.1320. So that's the denominator of our slope. If you can remember the slope is rise over run. Okay? And then for the y-intercept that we have here, this one is actually the mean of our dependent variable. So that's going to be the one here. Sorry. Yeah, that one there. And then this is the mean of our independent variable, 1.46, and this beta is from the slope here. Okay, we have to solve everything for the slope before we have that beta. So we now have our equation of the regression line here. Okay, and let's replace these variables here on these equations with the actual values. Okay, so if we divide these two, we're going to get a slope of positive 0.4925. Okay, so this line is sloping or going up towards the right because it's a positive slope. And then for the alpha or the intercept, let's replace this with the mean of our dependent variable minus beta times the mean of our independent variable. So our intercept, where our regression line crosses our y-axis, is at 0.281. Okay, so we can now assemble the equation of our regression line. So that's y equals 0.281, that's the y-intercept, plus the slope of the line, 0.4925 times x. So this is now the equation of our regression line. So this was our scatter plot from a while ago. Okay, so because the y-intercept is at 0.281, we can know exactly where our regression line crosses the y-axis, and that's exactly here, that point over there. That's 0x and 0.281y. Okay, and then using the concept of rise over run, so we are going to rise from 0.281, 1.05. Okay, so we are going to add 1.05 to rise up here. And then after that, we are going to run 2.1320 to the right. Okay, so our next point, therefore, is somewhere there, exactly, which is defined by the coordinates 2.132 and 1.331. And if we connect these 2 points, we have created our regression line. Remember, it only takes 2 points to create the line. Plus, we have our centroid that we solved in our previous video, and it should be exactly on the regression line. So if we are going to check if indeed this is the equation of the line, let's input the centroid, okay, the coordinates of the centroid with this equation of our regression line. Okay, so take note that these are the coordinates of the centroid, the one here, that's this, and then the 1.46x here, that's this 1.46, and we have exactly the equation of our regression line. So we can now predict the values of the mass lost in grams using our regression line. Okay, so using the equation of the line, we can simply input x and y's to predict the values of our mass lost. Okay, so for example, for the first data point here, okay, we simply replace x with 2.3, okay, as shown here, and then we can get the y, okay, and then we can get the y. This is what we're looking for. So the answer will be 1.41. So this is the predicted mass lost. Compare that with the observed mass loss that we had since the previous video. Okay, so they're a little bit closer now. And then we can continue doing this. Just input your x so that we can have y. And we have our predicted mass lost. Remember, in our previous video, our prediction was always 1 because we are constrained by our knowledge that we only know one variable at that time. Now we already know 2, and we have a regression line. And look at the difference in our predictions. Instead of just being 1 all the time, we have exactly precise predictions. Okay, so if we plot these predictions here, you can see that they are not much very different from the actual or observed values of mass lost. And so naturally, the next step is to see the errors between the actual, the blue-colored data points and the predicted values of the mass lost. Okay? And in order to do that, of course, we will subtract. Okay? These are the coordinates in y, okay, of the observed mass lost, and we are going to subtract the predicted mass from that. Okay? And then we are going to square. So we now have our sum of squares regression. So this is now our sum of squares regression. Okay? So as opposed to the sum of squares total a while ago when we did not perform linear regression, this one is a lot smaller in value. Okay? So if we now compare our two sum of squares, when we only were dependent on the chitin loss in the previous video, our computed sum of squares, the sum of squares total, was 0.54. And remember, we mentioned here that the goal of simple linear regression is to reduce this as small as possible. Okay? When we now factored in the second variable, which is our independent variable, the days of exposure to the bacterium. Our sum of squares regression, okay, went down from sum of squares total. It's now 0.0229. That's a very, very big leap, thanks to the second variable that we have considered. Okay? So if we subtract our sum of squares regression from our sum of squares total, we get a 0.5171. So this is the sum of squares total due to regression and was addressed by applying linear regression in using the independent variable. So thanks to our use of the independent variable, we are able to remove this error, okay, from 0.54 now to 0.0229. So 0.0229 of our sum of squares total were due to error. So take note that it's still not complete error-free result, because we still have a sum of squares regression of 0.0229. It might be a lot smaller than 0.54 originally, but it's still not zero. Meaning to say, this error here cannot be explained by our linear regression method, or it cannot be explained by the second variable, which is the days of exposure to serratia liquefaciens. Okay? So, not perfect, but at least we have reduced the error. So, in equation, our sum of squares total is equal to the sum of squares error plus the sum of squares regression. Okay? So, this one is the sum of square regression. Okay? This one is the sum of square regression. Okay? And then you have sum of squares error. If you add both of those, you're going to go back to the sum of squares total. Okay, so our coefficient of determination is the last point of why we are doing this. Okay, the coefficient of determination R squared. The coefficient of determination is just the ratio of your sum of squares regression and sum of squares total. Okay, so these are the errors that were addressed by our linear regression, the one in the numerator. And these are the total errors when we did not do linear regression. And the ratio of the two is 0.9576, meaning to say we have addressed 95.76% of the errors simply by considering a second variable, the independent variable, which is exposure time to serratia liquefaciens. Okay, so in conclusion, we got a Pearson correlation coefficient in our previous video of 0.97 or 0.98, and that shows a very strong positive relationship. Okay, and based on our linear regression methods, okay, we are able to compute for our R squared, okay, which is 0.9576, and this means that our linear regression is a good fit to explain the data set that we have. Okay, so we are able to explain well the relationship between these two variables, mass lost and time, plus we know that their relationship is strongly positive. So in the next video, we are going to try I'm going to show you how we can work in Microsoft Excel with linear regression and correlation.